comment? Okay, خلاص.
No, it was just by mistake. Sorry.
No problem. Bismillah, alhamdulillah, salatu wassalamu ala rasulillah. Here in this class, we want to give you an overview about the course contents, course scope, coverage, and how we will proceed in this course, inshallah. So the contents here is just a brief introduction or overview about the followings: artificial intelligence or intelligence definition, and also the artificial intelligence definition, different definitions of artificial intelligence. We will go over them quickly, and we will give you like a brief overview about the I don't know, Riyad Al-Aqili is asking, the Riyad Al-Aqili is here, or he sent a message, he need to be invited. Anyone knows Riyad Al-Aqili?
Yes, Doctor. He's in our WhatsApp group, so I sent him an invite.
Okay, great. So he can join the meeting now until we add him, okay?
Yeah, I believe so.
Okay. Right. The history of artificial intelligence, how the artificial intelligence started, and what are the different milestones for the artificial intelligence techniques that we have nowadays. Course structure, intelligent control techniques. As we mentioned, we have evolutionary algorithms, we have neural network, and this would be the last, and fuzzy logic, and hybrid systems. And we will give you just a brief overview about the differences between intelligent control and the classical control. Any major differences in a brief way, and also applications of artificial intelligence and the advantage and disadvantage of artificial intelligence. Okay. So what is intelligence? As we discussed last class, intelligence is the ability to comprehend, to think, to do some kind of reasoning, to learn from your experience, past experience. So the dictionaries define intelligence as the ability to comprehend, understand, and profit from experience, have the capacity for thought and reason. Other keywords that describe aspects of intelligence include creativity, skill, and I would like you to mute yourself if you don't have any question or comment. Consciousness, emotion, and intuition. And as we mentioned earlier, these techniques of artificial intelligence try to mimic the human thinking, human behavior, human response. Not only human, but also natural inspired issues also can be considered here, whether bio or physical inspired techniques or something, as we will cover during the course, inshallah. The artificial intelligence is coined, or this term specifically is coined in 1956. So John McCarthy coined the phrase of artificial intelligence in one of the conference in 1956. And the definition was use of a computer to model intelligent behavior with minimal human intervention. This was the definition at that time. Machines and computer programs are capable of solving the problems and learning from the experience or from training. You can train and extract the conclusions later like a human brain. And it is a science of and the engineering of making intelligent machines, especially intelligent computer programs. And it is not like classical codes. You have an input and you go through some of the equations and you substitute and then you have an answer. Classical codes needs, you should know the model of the process, the model of the system that you are handling. If you, in the classical way, you have to have the model. So you have some input variables and output variables. So you can have the input and get the output through the model. But here for artificial intelligence, we sometimes call this artificial intelligence are model free. And this can be, say here, model. Okay, model, what is it is in the opposite way. So you can say this is model free techniques. You don't need the model of the process. You just want to know the overall relation between input and the output, maybe based on experience and so on, similar to what we have in fuzzy logic. So these techniques are model free. It is not similar to the conventional codes. Yeah. It is related to the similar task of using computers to understand the human or other intelligence. And you can see now a lot of applications in mobile to understand the human. You can ask and then they can give you the answer and so on. So these are some of the artificial intelligence applications. Again, other definitions, the automation of activities that we associate with the human thinking activities, such as decision making, similar to the expert systems, you end up with a decision, problem solving and learning, the study of the computation that make it possible to perceive, reason, and act. Systems' ability to interpret external data correctly, to learn from such data and to use those learnings to achieve specific goals and tasks through flexible adaptation. So all these are different, definitions of artificial intelligence. So as we mentioned, the bottom line is that these techniques mimics the human behavior or bio-inspired techniques or natural explained techniques. So this is the some kind of historical background of the artificial intelligence. Started from 50, coined in 56, and then you have some, development in 81, and then you have some kind of this should be here before 81 anyway. But this is like a winter, first artificial intelligence winter where we have some reduction in interest of the artificial intelligence at that time. So the lose or the artificial intelligence lost the interest of the industries, but it come back in '85, and they start the research. This comes again to the second winter of the artificial intelligence. But since then, you have now computation facility, very high computation facility, or the computation facility becomes more mature, and this allow the people to go back to the artificial intelligence and develop. This is first artificial intelligence player was driven into the market, and this one is Deep Blue defeated the Kasparov in a chess game. And then you have other 2000, 2012. These are the major milestones in developing of artificial intelligence techniques in general. So as you can see here, now artificial intelligence will write essay in future, will mimic the musicians, and generate songs and videos in future. So the development is amazing. In this course, we will cover, as we mentioned earlier, three major topics: evolutionary algorithms, neural network, and fuzzy logic. Evolutionary algorithms, these are bio-inspired or natural inspired techniques. Genetic algorithms, evolutionary programming, differential evolutions, all these techniques have a common features. We will start with discussing the common features among these techniques, and later we will hit each technique and we identify what are the different operators that should be implemented in each technique here. Neural network, we will discuss the single layer perceptron, multi-layer perceptron, supervised learning, unsupervised learning, and radial basis function. And this part, most of you covered it in 555 course, neural network course. Fuzzy logic, we will see what is the fuzzy logic, what is the fuzzy sets operation, how the fuzzy sets is different than the classical sets, and membership functions. We will define the fuzzy inference system, how to start from the input measurements from the process. If you have, for example, a motor, you can measure the voltage, current, speed, and so on. So how can you use these inputs in order to control the motor at the end? So how to go from the input to the output through the fuzzy inference system, through fuzzification and defuzzification, how to fuzzify the inputs, and for the output of the fuzzy inference system, how to defuzzify it in order to have the interface to the real world. And we will see the fuzzy logic control through some examples, how to end up with the control signal to your process. If you have any question, don't hesitate to raise your hand and ask. Evolutionary, Hisham, sorry, Sham.
Sorry, Doctor. I know this is early question, but I wanted to ask, how can we evaluate this optimization method? How can we say this is better than others?
You mean the evolutionary algorithms? Or in general?
In general.
Definitely, usually in optimization, they developed some kind of benchmark problems. You have benchmark problems, standard problems, and the optimal solution is known. Yani they know, they give you a very complex function, and the optimal solution is known. And then you try these techniques, and then you can see which one gives you the nearest optimal solution, nearest to the optimal solution. Okay, so you can, benchmark against different techniques. But usually the comparison here is very, very difficult. لأنه each parameter, each technique here has some parameters, has some key parameters you have to play with. يعني for example, in genetic algorithm, you have what we call the two operators like crossover and mutation. These operators, they have probability, and you have to set the probability in advance or make them adaptive, maybe. So how to set the crossover probability or mutation probability? Is it 0.6, 0.7, 0.5? And you have to run each technique several times and until you reach to the optimal. And you have to do also some kind of statistical analysis. And for example, if this technique is considered, we can run it for 10 times with different settings, and we can do some kind of statistical analysis. What is the minimum value? What is the best value? What is the worst value? What is the average value? So we can know whether this technique is robust, that gives you very close answer, whatever the settings of the parameters or not. For these issues, we will discuss these issues from time to time. But anyway, there are some benchmark problems you have to test your technique against them first. But definitely, you can say, we have some problems associated with each technique, and these problems you can, for example, in genetic algorithm, you can have some what we call the premature convergence. This is one of the problem here is called the premature convergence. The genetic algorithm depends on creating children from the parents. And you have parents, it is bio-inspired. It's like human being. You have parents, and these parents produce 2 children or more, and then you can test the children against the parents, and they based on what we call the survival of the fittest. This is the principle, survival of the fittest. البقاء للأقوى، يعني شريعة الغاب. So this is the, if the child is better than the parent, then we eliminate the parent. طبعا the parent is a solution, يعني the child also is another solution. So if this better than this, so we will eliminate this one, and we keep the good solutions or better solutions with us from iteration to another or from generation to another. So in some cases, you can have all solutions are typical. And you have all the parents and the child are the same. There is no change. All the solutions come to the a replica of others. So this is what we call the premature convergence. Of course, we have some countermeasures in order to solve this problem, you have to disturb the generations, and you have to do some. There are some problems associated with this will be covered in details later on.
Doctor,
yes.
Quick question here. We look at, for example, the second layer here, like evolution algorithm, work and fuzzy logic as a separate, let's say, approach or techniques to different application, or we can combine let's say two, like neural network with evolutionary algorithm, we can combine it together to get reasonable results.
So your question is, would it be possible to combine one technique with another?
Yes, or we deal with them as separate according to a specific application.
No, as we mentioned earlier, we have what we call the hybrid systems. This hybrid systems could be neural network hybridized with fuzzy logic. You may combine these two techniques together, or genetic algorithm, for example, with neural network, or genetic algorithm or other technique, of course, in this category with the fuzzy logic. And that means, if GA is an optimization technique, you need to optimize neural network. And if you study neural network, and you know the training of the neural network is to find the weights and the biases, right?
Yes. Yeah.
So, and you find the weights by the back propagation or gradient descent method, right? This is an optimization. You are trying to find the optimal weights of the neural network in order to minimize the error. So if you apply genetic algorithm to optimize the weights of the neural network, not by back propagation, and you replace the back propagation by genetic algorithm. You don't need to have the gradient and the back from one side, from one layer to another, but you can use a genetic algorithm to optimize the weights of the neural network. Here in fuzzy logic, you have what we call the membership functions. Functions, and these functions have some control parameters. So you can also apply a genetic algorithm to optimize the shape of these, membership functions. So you can optimize them with the genetic algorithm or any other technique here. Of course, you can combine also the neural network and the fuzzy logic. That's what we call the ANFIS. Adaptive Neuro-Fuzzy Inference System. This is, you have the input of the neural network here, and each input you fuzzify it. You have here one rule 1, rule 2 of the fuzzy logic, and also you fuzzify this inputs, and so on. You proceed here and so on. We will also discuss this ANFIS. Probably we will show you the structure of the ANFIS in this lecture also later on when we discuss such techniques. Of course, you can hybridize any two techniques, or you can hybridize the three techniques together. Okay?
Okay, clear.
Okay, great. So evolutionary algorithms, genetic algorithm, and differential evolution, particle swarm, and so on. These are bio-inspired or natural-inspired techniques. And for example, this is the survival of the fittest principle. and also the swarm behavior, maybe fish schooling and ant colony, artificial bee colony, all these swarm intelligence can be also inspired here. And also physical, if you have lightning search, and how this lightning stroke reach to this one, what is the shortest path to the ground here? So how this will propagate to find the shortest path here. So this one also is the physical phenomena that you can inspire and implement this to the optimization problem, so the solutions can get benefit of the behavior of this physical phenomena. And also for harmony search technique for music, and then you can also find the harmony or the best harmony approach here. So these techniques are bio-inspired, swarm-inspired, physical-inspired, and these techniques has a common feature, whether genetic or particle swarm or whatever. Usually, these techniques are called the population-based techniques. Population-based technique. What is population-based? And usually in classical optimization, you start with one solution. And maybe the problem you can just guess what is x0, and then you by iteration you get x1, you get x2 with iterative techniques in order to get the optimal solution. And sometimes you can have the technique itself is sensitive to the initial solution. Maybe if you start with one solution, x0 to end up with مثلا for example different solution. If you start here with another solution for another trial, then you can end up with a different solutions. Or you can even find the solution or the technique diverge, not converge. These technique, classical optimization may depend on the initial guess that you give. Here, in these techniques, you start with the population of the solutions. Not only one solutions, but you can create, at the beginning, you can create 10 solutions. And these 10 solutions will be handled simultaneously. And also you can have 100 solutions, or it depends on the complexity of the problem. If you have 10 solutions, initial 10 solutions, so this is the population. So for the first iteration you have 10 solutions, for the second iteration you have another 10 solutions, which should be an improved version of the initial solution. And you are improving the solution from generation to another. So these population-based techniques, if you start with 10 solutions rather than one solution, most likely you will reach to the global, حتى دول بيسموهم global optimization techniques. And if you look at the MATLAB, these techniques are gathered in global optimization. And here, if you have this function, for example, if this is the function, and we need to find the minima or the minimal value. So if you start here, you will end up with this point. And you will get trapped here in local minima. This is local minima. This is local minima. This is maximum, or this is a global, the global minima. This is the global minima based on this figure here. So if you start here for the classical, you will end up with this point, and you will not move forward. And if you start calculating the gradient, you are approaching this one. And here, no, you will go back to, you will oscillate in this, and you will end up will be trapped here in the local minimum. If you start here, if you are lucky, and x0 is here, the first initial guess, you will be lucky and will you finish here in global minima. If you start here, so you will end up with this point. So the classical optimization techniques are sensitive to the initial guess, and if it reaches to the local minima, in this case it will be trapped here. But if you start with the population of the solutions, if you start with 10 solutions, you start with the solution here, solution here, solution here, and solution here, and so on. So most likely you will reach, you will reach this solution definitely is better than this solution, for example. And this will give you a minimum value or lower value than this value of the function. So when you from iteration to another, you can go to, most likely you will end up with the global minimum. And the beauty also of these techniques is it is they don't depend on the gradient, and you don't need to get the gradient or to differentiate the objective function, and also they are not sensitive to the linearity. Maybe for the linear programming you have to have linear functions and linear constraints and so on. But here, whatever the objective function, whatever the constraints, continuous, discrete, smooth, non-smooth functions, whatever the function, you can solve the global optimization here. So these are you start with the initial evolutionary algorithm here, and this is usually the procedure, and you initialize a population of individuals. You create here 10 solutions randomly, and then you evaluate the fitness of all individuals. You calculate F1, F2, F3, F4. At all these points, you calculate the functions, and then you can select the parents here. What are the best solutions here? You can say, okay, this solution is better than this solution, right? So let us take this into consideration in order to produce other solutions later. We will take them for the mating pool, and to generate other children, other solutions. So you can select here, you do some kind of selection here. You select the better solutions to be the parents for the next generation. And then these parents, you will make them together. You will combine some features from that solution to that solution. You will do some kind of crossover among the parents. For these parents, this is the solution. You have x1, x2, x3, x4. These are the parameters. And this is x1 prime, x2 prime, x3 prime, x4 prime. These are the optimized parameters in the second parent. Then you can do some kind of combination here, and you can shuffle some of the features. You can replace, let us take this x1 from the parent here, and we put it here, and we move this x1 prime up to this solution. So now we have two different children, and maybe these children will be better than the parents. So you can you do some combination of the genes. Let us say this is a chromosome, and these chromosomes have some different genes, and then you can switch the genes here from the two parents, and then you can create different solutions or children. And then you can do also another operator here for the you can perturb this population by suddenly change of any of the gene. If it is 0, then you can put it 1. If it is a continuous variable, this x, مثلا, for example, x1 ranges between 0 and 100, and you can start again, you can check, you can replace this x1 by any random number between 0 and 100. This is the simplest formula for the mutation here. You do some kind of sudden disturbance of the solution. Hopefully, this sudden disturbance can lead you to better solutions later on, or can give you a bad solution. So it could be either way, and definitely the bad solution will be eliminated in the next generation and so on. So these are generally the procedure. You start with the population of the solutions, and then you evaluate each solution based on your objective function. And in this case, you can select the better solutions, and then you can combine these solutions to create children. You can do some kind of sudden disturbance of a solution or so, and then you can check the termination criteria. If the solution is satisfied, you are satisfied with the solution. If you reach to the maximum number of iterations, then you can stop. Otherwise, you can go and evaluate the new solutions after the combination and the perturbation, and calculate the fitness, and do combination again and again and again until you reach to the optimal solution. So this is generally the procedure. And this is generally the procedure of the evolutionary algorithms. Do you have any question? Do you have any question? Hisham Muhammad?
Yes, Doctor, I just wanted to ask, can we say that the wide range between points will lead to the global minimum?
Can we say what?
Wider range between points lead to global minimum faster than the short range.
What do you mean by wider range and short range?
Between the points. First of all, this genetic algorithm will take that, will spread out points through the graph. So can we control the range length between these points, or we cannot?
لا هو actually you mean this range, for example? You mean this range, or طبعا this range is related to the problem itself, and this is a variable in your process or in your problem, and this variable takes the range between 0 and 100, so we cannot touch this one. When you say here, if you are asking about the range here, of course, if you minimize the range, if you limit the range here up to this point, so this is your range that you are searching in this case, you will end up with this as a global minimum. Then you are not seeing all these portion of the function. Okay. Did I answer your question, or?
Yes, but this would lead to complicate the problem, or it will not do?
لا, it will not do. يعني أنت you have a function and you need to optimize it. Definitely, yeah, the point is, if you don't, and for example, let us say in control, if you have BI controller, KB plus KI over S, and you want to design this control based on intelligent techniques here. So how much KB? How much KI? What is the range? These are the optimized parameters. This is X1 and X2. And KB, what is the range of KB that you will search in? What is the range of KI that you will search in? This is the problem. This is the challenge here. But in this case, what you can do is you can start from minus infinity to infinity. Very small value to very high value, negative, positive, right? And then based on the experience, you run the case and you end up with KB, and sometimes KB goes to 50 مثلا, for example, and the KI goes to مثلا 2. So based on this wide range here, you end up with this solution. طيب, يبقى this is the promising area, and this is the potential area of KB and KI. So let us go plus minus a percentage of this 50. Let us start from 0 to 100 now. So let us close. Let us let us shrink the search space around these points, and then you can find like more better solution around these numbers. So you can shrink your research space, and you can focus more on this area. So it needs some experience about your problem in order to set exactly the range that you are looking in. Is it clear?
Yeah, now it's clear for me. Thank you, Doctor.
Okay, thanks. Salim Ghanem?
Yes, Professor. Just I want to ask about the classical optimization theory for convexity and non-convexity. I mean, the underlying function, whether it's convex or non-convex, does this matter? Does it make any difference for this evolutionary algorithms? Will we reach to or converge to the solution eventually?
This is a good point. As I mentioned, this evolutionary algorithms is not sensitive to the function or to the search space, whether it is convex, non-convex, smooth, non-smooth, continuous, non-continuous. It doesn't matter. You can see here, for example, if you have a function like this. Here. This is the function. Function here is discrete or non-continuous function, right? It's non-continuous function. مظبوط ولا مش مظبوط؟ This is uncontinuous.
مضبوط دكتور.
So this is the local minima and this is the global minima. If you start somewhere here, you will be trapped in this one. This is the classical optimization. But if you start with the population of the solution here, solution here, solution here, solution here, so you will reach to the global optimization. So it doesn't matter whether the search space is convex, non-convex. It doesn't matter with the evolutionary algorithms. It matters definitely with the classical optimization. The search space should be convex, but here this condition is relaxed. a lot of conditions actually here is not there. As I mentioned, differentiable or linearity or non-linearity, differentiability or non-differentiability, smoothness, and so on. So these solutions are very robust, and there is no restriction on the objective function, on constraints, on search space, on whatever. I hope I answered your question.
Yeah, thanks, Professor.
Okay. So any other question? No. Type. A neural network, which will be probably this will be the last part in the course. It mimics the human brain, the learning process of the human being. And the neural network, this is the bio-neuron or biological neuron. So we try to mimic this neuron in a mathematical way and see how the neural network behaves. So you have neural network, you have inputs. These could be the measurements of the process. And then you do some computation through some structure here of neurons, and it gives you the output. And this is the relation between input and output. It has nothing to do with the modeling of the process. It is a model free. It depends on the input and output. If you adjust the structure here in order to improve the accuracy of the output in the learning phase, or you have some kind of training phase where you expose, let us say, the supervised learning. So you start here with different or random structure or random variables here. And you check the output. You have the input and you check the output. But for those inputs, you know the target value. You know the actual value based on the process. You compare this input with this output of the network with the target value. Okay, you have a process, you have a system, and if you know the output, if you know the input, you can through the process or through the modeling of the process, you can find the output. So this becomes the target. And for this random variables here, when you expose it to the inputs, it will give you rubbish here. It will give you very different values here. But based on this error between the actual value or the target value and the actual output from the network, you can have the error here, and you use this error to adjust the weights here, to adapt the weights here or the variables here in order to improve the output of the network, and the error will reduce with time. You expose the network again to other set of inputs, and then you adjust the weights and you reduce and so on. You repeat this process several times for the training phase, and then after training phase you can test your your network, and if you are satisfied, you can take it to the field. You can implement it through microcontroller or any real-time platform, FPGA or whatever. And so this becomes like a process. You put the input and you get the output right away in no time. So you can, use its output as representative to the model, to the process itself. Of course, this could be not only to model the process, but could be a controller here. And you can have like a classical controller, BI controller, KB plus KI over S. So this is the input, this is the deviation, for example, delta omega, and this is the control signal. So you can adapt this KB and the KI with, you know, if you have here your system. For this system, you can cover a wide range of operating conditions. يعني for example, for a DC motor مثلا, DC motor, you know the voltage, the input voltage, and you can see here the speed omega, okay? And if you have even flux or something here, you can, whatever. Yeah. So based on a certain change in the output, you can design a BI controller, KB plus KI over S, and then you have it here. So for each operating point, you can have a different value of KB and KI for each operating point. Is it true?
Yes.
Of course. If you have any system, you linearize the system around an operating point, and then you can find the controller. And this controller is, you know, is designed based on this specific operating point. But if you scan this, if you change the voltage here from 100 to 150, and for each point here, you can take 10 points, for example, and each point you design KB and KI, which behaves better in this specific operating point. So you have different operating point, different voltage, مثلا, for example, input, and the output is KB and KI. For each input, you design KB and KI. For each input, you design KB and KI, and so on. So this neural network can give you here the best value of KB and KI. You can design like an adaptive controller. And the KB is not fixed, but you can measure the input here, which is the voltage. And based on this voltage, the neural network will give you what is the value of optimal KB that fits well with this voltage level, and what is the value of KI. And if the voltage here is changing, then you can find adaptively KB and the KI. So you can have some kind of adaptive controller using this neural network. So neural network is a relation between input and output. It is model free, and you can have the variable here, and these variables are, we call it weights and biases. So you adjust the weights in order to have the best performance, and then the neural network could be implemented in real life. So this is the structure of the neural network in general. You have input layer. These are the input layer, and these are the output layer. And you have here hidden layer. You can have one hidden layer, you can have two hidden layer, three hidden layer. And the learning process is to find how much is the weight of this link. How much is the weight of this link? How much is the weight of this link? How much is the weight of all these links? So here is the learning process is embedded in these weights. So this is the structure of the neural network in general. And the training neural network means finding these weights. Okay. Any question? Hisham Muhammad, please.
Can we say that, Doctor, can the neural network use B to identify the system?
Again, your question?
Can neural network be used to identify the system?
Identify?
Yes, if we have the input and the output, and we don't know the system.
Yeah, it behaves like a system, yes. And you can have it is similar to the system. And if you have a system here, this is your system, and you can build like input-output model for your system. This is the input, and this is the output. So this is the actual output. This is the target output. You can have the neural network here. You expose it to the same input, and the output here is, can be compared. And if you have an error, this error would be used to adjust the weights here. So once you reach to a satisfactory, state, in this case, you can say, this neural network now behaves as this system. Of course, you can represent the neural network as some kind of function here. And these are the inputs. The inputs are multiplied by the weights. So you have an input X multiplied by the weights. And these weights, you have here some activation function. You have different activation function. We will discuss these functions later on. So you apply this function here of the input, and you get the output, and this output will be multiplied by the weight here, and then you have here another activation function, and then you have some weights here, and the output of this neuron will be multiplied by all these. And you can, at the end, you can have some mathematical representation here of the system. Okay.
But this mathematical representation, it will be a linear. So.
Not linear. This activation function is non-linear. You may have non-linear activation function here, and this function is not necessarily to be linear function. It could be a non-linear function, and you can have a sigmoid function. This is 0 and 1, and you have it here. You can have hyperbolic function. You can have a binary function, even you can have like this function. This could be a function. You have some nonlinearity here. Yes, it is not. Just linear multiplication of this and that. But here the activation function could be nonlinear. So this is the way. Yeah. Okay.
Okay.
Fuzzy logic and the fuzzy logic control, it uses the same language as the human use. Some of our discussions or judgment or measurements are somehow fuzzy. Fuzzy means vague. Fuzzy means vague, imprecise. So when we say, for example, the temperature is high, temperature is high. Such a sentence is vague. It is not like crisp value. High here is maybe has different meaning. High for you is not high for me. How high is high? Okay, so you have here some vagueness or imprecision. So we need this temperature here is called the fuzzy variable, and the high here is fuzzy value. And you can say مثلا temperature is 40 مثلا degrees centigrade. خلاص, this is the crisp value, and this is specific value 40 degrees. إنما high means what? طيب لو if we consider 40 as high, طيب 39 degree تعتبرها ايه؟ You consider it what? High or low? Or يعني somehow is approaching high, يعني you know, but يعني in general in mathematical sets 39 is not high. خلاص, this is the classical way, is not high. And if this is the set of the high temperature, if 39 is here, خلاص يبقى 39 is not belonging to the set, so it is not a member in this set. But in fuzzy logic systems, the change between these values is not abrupt change. It's not crisp change. It is a vague. That means this set is doesn't have hard limits here. This set is gradually changing the membership. And you can say this 40 here is higher than 40. 40 or higher than 40, this is 1. It belongs to this set. But if it's 39, you can say it belongs to this set by 70%. مثلا. And if this limit or the end here is مثلا, for example, 20 degrees, if below 20 degrees is 0. Doesn't belong to the set high. Number 20, 21, 22, they are member in this set, but the membership value is different. Maybe this is 0, maybe 25 is 20%. Maybe the membership of 39 is 95% or 0.95 belong to this one. So the you know, the fuzzy sets are not, or the fuzzy the uncertainty in our decisions and our judgment is considered here in fuzzy logic. So if this is the process, you have some measurements here, and these measurements goes to these are numerical values. Your measurements, you measure the speed, you measure temperature, you measure pressure, you measure whatever variable here. So these are numerical values. These values will be fuzzified here. For example, if the speed deviation is 0.1, maybe 0.1 that is low. So we convert this 0.1 to low. We measure the membership of 0.1 with the set of low deviation or low error. So you fuzzify these numerical values, you convert it to linguistic values. So this is the fuzzification step. And then you have some kind of if-then rules. If-then. If the deviation is low, then my action is to increase the voltage by low increase in voltage. If the deviation is high, then I have to increase the voltage input. مثلا, this is a DC motor or whatever. So these are if-then rules. Will take these linguistic values, and these linguistic values will fire these rules and you combine all the rules here will give you some linguistic decision, and this linguistic decision will be defuzzified, will be converted to numerical value here, and then this is the output of the control, so you can go to the process again and measure and so on. So this is the fuzzy logic controller. You take the measurements from a process and you interpret these deviations as linguistic variables or linguistic values, and based on the if-then rule, based on your experience or based on the operator experience with the process, he knows, you know, if this deviation is high, then I have to take this action. If this is low, then I have to increase this. For example, in any discipline, you will find out such issues. Maybe in electrical engineering or in power system in general, if the voltage is low, then I have to increase this capacitor or whatever transformer taps or whatever the tools that we have in this specific area. So this is the process. If then rules here are embedded and based on our experience or operator experience, so when we measure something, we fuzzify and then we defuzzify the action and go back to the process. So this is simply the fuzzy logic controller. And as I mentioned, you know, the fuzzy depends on fuzzification. What is the fuzzification? Fuzzification is to convert the measurement to linguistic value rather than a crisp value or numerical value. So this is the classical definition or non-fuzzy definition. This is the classical set. If this is the pressure, masalan, for example, if this is the pressure, if it is below 5, then it belongs to this set. If it's greater than 5, then it doesn't belong to this one. So you can see here an abrupt change of the classical sets, either belong or not belong, either 0 or 1. If you have any value here, this value, its membership either 0 or 1. 0 doesn't belong, 1 belongs to this set. But here for fuzzy, these gradually change. This is the limit, but this is the boundary. But as you can see here, the boundaries gradually change. So if it is below 5, let us, for example, here, if this is 5, it is below 5, this is in 1. But if it is higher than 5, it still belongs, but the membership could be 0.75 instead 0.5. And when you reach here, the membership becomes 0. So such a set has some kind of if the value here, then the membership is 1. If the value here is the membership is 0, doesn't belong to this set. But if the value here, so the membership is anywhere between 0 and 1. It depends on the closeness of this point to the set here. Okay, so you can you can have different sets. You can have cold, warm, hot. You measure the temperature. If you have a temperature here, for example, if this is the value, these are the measured value of the temperature. So this measured value of the temperature has a membership of warm and also a membership in cold. So it is, with different membership. Here is membership probably 0.2, here is 0.8 or something. So of course, when you go to if-then rules, you can have if the temperature is warm, then you have to take this action. If the temperature is cold, you have to take this action. And based on this membership, we will see what kind of computational process we will do in order to come up with the conclusion or output later on. So, Sharif Ibrahim, do you have a question, Sharif?
السلام عليكم دكتور. Doctor, regarding fuzzy rules, I know, as you mentioned, it is based on the expert or the experience of the designer. But is there any easy method or easy way to assign this rule? When we talk, and you mentioned this temperature example, warm, cold, hot, but related to control design, if we say KB, KI, and error, so is there any easy method to assign these rules?
Okay, if you have experience with your system, or if you collect the experience from the operator of the process, that's fine. You have if-then rules. Okay? Is it clear?
Sorry, doctor, the voice is cutting. I'm sorry.
I mean, if you have experience with your plant or with your system, then you can develop the if-then rules. Okay?
Yes.
Is it clear now?
Yeah, it is clear, but I talk about.
I mean, the voice is clear.
Yeah, it's clear, doctor.
Okay. So if you have experience, that's fine. If you don't have, what you can do is either you go to the operator of the plant, or the more experienced people, and then you can, put their experience in if-then rules. If you don't have, then you can create it. Here the temperature, for example, we can say this temperature here is 40 degrees, and this is 60 degrees, and this is a little bit 80 degrees, and this is 100 degrees, for example. And these values can be randomly set, but you can implement other optimization techniques to give you the optimal values of the starting of this worm and the ending of this worm, and even the shape of this membership function. This is a membership function. We call it in fuzzy logic literature. This is a membership function. It's not only trapezoidal. You can have it like triangular. You can have it like Gaussian. These shapes can be optimized. These cut points or key points here, or key parameters here for this function also can be optimized. And then you can have this hybrid system, as we mentioned earlier. You can implement a genetic algorithm to fuzzy logic, to design the fuzzy logic system. Okay? I hope I address your question.
Doctor, yeah, it is clear. I have another two questions, if you allow me.
Okay, go ahead.
Doctor, you mentioned that either from the previous work or from the literature review, you can see the rules, or you can create it. Okay, if I create it, for example, if I put very large or medium for a specific rule, for example, so how can I check I do the right way? This is my first question. My second question, you mentioned that the shapes, triangle and trapezoidal. If the type of shape make a major difference, in at the output of the solution or the results. This is my second question. Thank you, doctor.
Well, the point is, the shape doesn't affect much, but it can improve the performance. And حتى even it shouldn't be symmetric as you can see here. Maybe it could be non-symmetric. Maybe this مثلا membership function gives you, you can see here, this membership function is not symmetric in view of this one. And you don't have, I mean, these parameters, the key parameters here of the function, the shape of the function, you are trying in order to find out the best performance of the system. It doesn't affect much, but it improves the performance of the system. Okay.
Yes, okay, doctor.
Okay. طيب. Next, Hamoud.
Yes, Dr. Hamoud. Yes, Doctor. Doctor, I have a question regarding the fuzzy optimization. You said, Doctor, for each uncertain variable, we have to make a membership function. And this membership function from 0 to 1. So we have to decide the upper limit and lower limit for each value of the variable. Yani maybe I have the value of the variable maybe 40, for example. So I have range مثلا the upper limit, let's say from 39 to 42. How can I decide the upper limit and lower limit for each variable?
This is this is your experience with your system. يعني أنت مثلا for example if you have any process like DC motor مثلا, this is a motor. You have an input here voltage, and you know the voltage is ranging between 100 مثلا to 150. Okay, you can create. This is the universe of this course between 100 to 150. You can say no at 100 up to 110 مثلا, this is low voltage, and then you have gradually change here to 120. This is 110. And then the voltage again will be low between 110 to 100 مثلا, for example 30. Voltage will be normal between 120 to 140. Voltage will be high between this and up to 150. So the range can be designed based on your experience. You can have 3 membership function, 5 membership function. It depends on the accuracy that you need. We have also what we call the scaling factors. And usually when we go to make it a systematic way, we need to limit the range here between -1 and 1. So you can have a scaling factor to scale the voltage between -1 and 1. So you can normalize the value of the voltage. So all these settings will be discussed in details when we discuss the fuzzy logic. So these values, based on your experience, you can set, and you can scale it. حتى مثلا if you measure temperature مثلا of a process, you know the temperature range from where to where. If you have مثلا speed مثلا, if you measure this speed, the speed of this, you know the speed of the
yes.
But you know the minimum and the maximum, and you can have this range, and you can discuss You can.
You're right, Doctor. But sometimes we use uncertain data like wind, and when we predict the wind for next year, we have some fuzziness, part of fuzziness in data. So we made a membership function. This membership function, it has to calibrate the optimal value that could be for the objective function. You understand me, Doctor?
You can optimize it. You can implement some optimization techniques. In this case. You can implement optimization techniques even to give you how many functions that you will use, what is the shape of each function, and what is the range of each function. All these can be considered as optimized parameters, and you can optimize all these parameters, shape, number, the key parameters of each function.
Okay.
Yeah.
Okay, understand. Thank you, Doctor. Thank you so much.
Thanks. So let us move to the next, Nasser Hakami, please. Nasser?
Yes, Doctor.
Yeah, please.
Setting these values like a 0.8 and 0.2, for example, or whatever, setting the range, this is a part of the human interface. So is it a part of our solution to readjust these values always manuals based on the experience as you mentioned before, or it can be a part of the intelligent solutions that it readjusts the values?
Now, this is the point. If you are very experienced with your system or your plant, then you can set the optimal values based on your experience. If you don't have, then you can optimize.
So knowledge is important here.
No. What did you say?
Knowledge.
Knowledge طبعا knowledge based. Fuzzy logic is a knowledge based. You have a knowledge based here. And this is the knowledge based. This is if then rules, and then when you measure something, then you convert it to linguistic values, and you compare it with the if then rules here and then stored here in knowledge based, and you take your decision based on this. And this decision will be defuzzified again to convert it to numerical values. So this is the control output. So the control output is a numerical values, goes back to the process. You have to have a knowledge base. You have to have if-then rules. This is the knowledge base.
Okay. Yes.
Any other question? Sharif is still raising your hand. Do you have any other question? Sharif.
Sorry, Doctor, I forgot to remove it. Thank you so much, Doctor.
Nasser Hakami, do you have? Okay.
Yes, I still have one more question.
Okay, go ahead.
When we said this is the global and the neutral and fuzzy, all they are free model you can consider. Is it really a free models, or it is a multi-model and then our model select what the best of all, or make the combination?
It should be one model, and if you need to check other different models and you optimize, you check for the optimal value or optimal one, so you can do this.
No, what I mean, for example, in linear optimizations, we have models and then we have certain step input output. Everything is going straight ahead.
Yes.
But in for example, in neutrals, we have multi-stage and then different options, different weight. This selection is again we have to adjust ourselves, and then we have to make all these scenarios. So again, we are modeling ourselves. It's not something it's modeled by the programming we are doing. So it is only extending with respect to the linear optimizations, just we are extending our range of solutions and input and methods.
Well, I don't know whether I get your point, or I'm not clear about your point also, Nasser. يعني, if you have then roles, you have, for example, 50 roles here.
Yeah.
50 roles. Okay. When you have an input and output, when you have an input here, you will fire a part of these roles, not 50 roles, but maybe 4 or 5 roles, 5, 6 roles will be fired. And based on these rules, you'll take the output will be dephasified here. If you have other inputs, temperature is high or temperature is low or cold or hot or something, then the values here when the values here is different, then the other set of rules will be fired, and you have different outputs here. I'm not sure whether I address your question or not.
Most of it, inshallah.
Yeah, okay. يعني على العموم احنا يعني we will discuss fuzzy logic in details. يعني if you have any question or يعني we can discuss it later on. The time is over by 10 minutes, by the way, or 15 minutes, isn't it?
Yes.
Please remind me, and I just look at the clock of the watch, and then I see it's 9:38 now. So please, remind me if the time exceeded. Okay. Do you have any question? If you have any question, please stay. Otherwise, you can leave. If you have any question, please raise your hand. And if you don't have, then you can leave the class or leave the meeting. طيب, Salim Ghanem.
Yeah, Professor, just a general question about the content of this course and the classical method. Is it safe to say that the classical methods are all used for benchmarking, but we can somehow, say that it's phased out in the industry?
لا, طبعا still classical methods. يعني if you have linear function, if you have linear constraints, linear programming is straightforward. Okay. Still, of course, the classical techniques are used in industry. Not only for benchmarking, but maybe the problem nature or the nature of the problem is very suitable for any other technique. And these techniques are very fast, by the way, and robust, or technical or mathematically proved. Okay, so still linear programming is used, quadratic programming, stochastic programming, mixed integer linear program. All these techniques are still used. They are very fast, but they have also shortcomings. As we mentioned, the restriction on the objective function and constraints, and all these restrictions are, relaxed here with these intelligent techniques. Again, trapping a local minima, this is the major problem, and also the convexity of the search space is a condition, but here no need to be worried about all these restrictions.
Yeah. Okay, thanks.
Okay. Any other question? If there is no question, please leave the meeting.
الكلام ده
Doctor, I have a simple question. If
Okay.
Doctor, regarding the my first question, you said